In electronics, you'll encounter an endless variety of circuits, each designed to do a specific job. Regardless of how complex they may seem, all can be reduced to a simple circuit. To prepare you for more advanced circuitry, in this lesson we'll review two basic types of circuits: series and parallel resistive circuits. To begin, let's establish the requirements for any practical electronic circuit. A circuit should contain a power source, fuse, switch, and a current limiting device. These components are connected with conductors, and when the switch is closed, current flows and the circuit performs work. In this circuit, current flows from the negative terminal of the battery through the fuse, the bulb, through the switch, and back to the positive terminal. There's only one path for current, so this circuit is a series circuit. If another bulb is added out here, we create an additional current path and change from a series circuit to a parallel circuit. Current now divides at this point, some going through this bulb and some through this bulb. Remember then, a series circuit has only one path for current. A parallel circuit has more than one path. With this in mind, let's change out circuits and look at the other characteristics. And we'll start with a series circuit. Let me make the power connections and close the switch. We should recognize this circuit as a series circuit. There's only one path for current. This means that current must be the same in all parts of the circuit, and we can verify this with the ammeters. We find that the current here is 200 milliamps. The current here is 200 milliamps. And the same 200 milliamps returns to the power source. Remember then, the same current exists at all points in a series circuit. Since the same current flows through each component, the total opposition to current should be the sum of these two resistors. If we ignore the meter resistance, which is very small, the resistance in this circuit should be 60 ohms, the sum of these two resistors. Well, let's use the ohm meter and verify this. I'll set the function switch to ohms, and we'll use a range of ohms times 10. And remember, anytime you're using an ohm meter, you must check meter 0 before you use it. Okay, meter 0 is all right. Now remember, when you're using an ohm meter, power must be removed. Now, I'll remove power from this circuit by opening the switch. Now, to check total resistance, we can connect one lead here and the other lead here, any place in here, as long as we're measuring the sum of these two resistances. So let's go from this point and this point. Okay, you see we get a reading of 6. The needle is right on 6. Now remember, we're using a range of ohms times 10. So we multiply 6 by the range switch setting of 10. We get a total resistance of 60 ohms. Okay, remember then, the total resistance of a series circuit is equal to the sum of the individual resistances. Next, let's check the voltage drops in a series circuit. According to Kirchhoff's voltage law, the applied voltage will be dropped around each closed loop. In this circuit, this means that the applied voltage will be divided among these two resistors, and the sum of these voltage drops will equal the applied voltage. Let's use the PSM6 and check this out. We'll set the PSM6 to the DCV function, and we'll use a range of 50 We'll use 50 since the applied voltage is 12 volts, so we're being safe. Now remember, we must observe polarity. So I'll place the negative lead here, next to the negative terminal of the power source, and the positive lead here. You see we get a deflection, but it's small. It's very difficult to read on the 50-volt range. However, it is less than 10 volts, so it's safe for us to decrease the range to 10. Okay, you see that we get a much more accurate reading. Now, on the 10-volt range, we use the bottom numbers of the DC scale. You see that we get a reading of, well, it's about 4.3 volts. 4.3 volts across this resistor. Okay, let's go down and measure the voltage here. Okay, here we get about let's call it 8.2, the bottom numbers on the DC scale. Okay, we have 4.3 volts here and about 8.2 volts here. If we add these two voltage drops, their sum is equal to about 12.5 volts, or somewhere near the applied voltage. And of course, this satisfies Kirchhoff's voltage law. Okay, there's one other thing to consider about a series circuit. This is the power dissipated by the components. You should remember that when current flows through a resistance, power is dissipated. As these formulas indicate, the amount of power dissipated is directly proportional to current and directly proportional to voltage. Any of these formulas can be used to find the power dissipated by a resistor in a series circuit. The total power dissipated in a series circuit can be found by adding the power dissipated by each component. Here are some important points to remember about a series circuit. There's only one path for current. Total resistance is equal to the sum of the individual resistances. The applied voltage is equal to the sum of the individual voltage drops. And total power dissipated is equal to the sum of the power dissipated by each component. Next, let's go over the characteristics of a parallel circuit. Now, we've changed out trainers so that we've added a parallel circuit here. Let me close the switch. First, we should notice that this is a parallel circuit because the components are connected in such a manner that there's more than one path for current. Total current will flow from the battery, and it'll divide at this point. Some will flow through this branch, some through this branch. We should also notice that each branch is connected directly across the power source. Then the branch voltage, each branch voltage, is equal to the applied voltage. This is obvious, so we won't have to verify it with the meter. Now, let's look at current in a parallel circuit. Since total current divides at this point, divides among these branches, it should be obvious that if we add the branch currents, we'd have total current. Let's check the ammeters to see if this is the case. Here's total current leaving the battery. It's 300 milliamps. The current through the first branch is 200 milliamps. The current through the second branch is 100 milliamps. And here we see that 300 milliamps returns to the power source. We had 200 here, 100 here. Their sum is 300, the total current. Also, we should have noticed that the branch with the smallest resistance had the largest current. Naturally, then, the branch with the largest resistance has the smallest current. So far, the characteristics of a parallel circuit are pretty obvious. The next one, total resistance, isn't. Let's see why. The circuit contains a 60 ohm resistor and a 120 ohm resistor. To find the total resistance of these two, let's use an ohmmeter. So we'll go to the meter, set the function switch to ohms, and we'll use a range of ohms times 10. And as always, we must check meter zero before using an ohmmeter. Touch it up just a little. And as always, before using an ohmmeter, we must remove power from the circuit being tested. So I'll open the switch. Now, to measure total resistance, I'll connect one lead here and the other lead down here, like this. We get a reading of 4. We multiply 4 by the range switch setting, 10. We get 40 ohms. The meter tells us that total resistance is 40 ohms. Total resistance is smaller than either of the branch resistances. But why? I have a simple demonstration that should show why. Suppose that these two blocks are carbon resistors, each representing 10 ohms. Well, when we studied resistors, we learned that the resistance of a material is directly proportional to length. If we connect the resistors end to end, as we do in series circuits, we increase the length of the material and increase resistance to 20 ohms. We also learned that resistance is inversely proportional to cross-sectional area. If I place the resistors like this, I've doubled the cross-sectional area of the material. This decreases resistance by 1/2, so we now have only 5 ohms of resistance. Well, this is what happens to total resistance in a parallel circuit. By placing the resistors in parallel, we increase the cross-sectional area. Total resistance, then, is less than the smallest branch resistance. If you'll recall, we measured a total resistance of 40 ohms in this circuit. Now, of course, the more resistors we add in parallel, the more the total resistance will decrease. Now, several formulas are used to calculate total resistance in a parallel circuit. This first one is used when there are only 2 branches in the circuit. In this case, we have R1 of 5 ohms, R2 of 10 ohms. The formula is the product of the 2 resistors divided by their sum. You shouldn't have any problems working this type of formula. Simply insert the values into the formula, get the product, divide it by the sum. Now, in some cases, there may be more than 2 resistors in the circuit, like this. So let me add a value for the 3rd resistor. Let's make R3 20 ohms. Now, when you're working this type of circuit, you use a reciprocal formula. This one. In this case, we have 5 ohms, 10 ohms, and 20 ohms. They're all different values. And when you're working this type of problem, you use this formula, and before you begin, you must remember to get a common denominator here. In this case, since we have these values, the common denominator is 20. After you've reduced each fraction to a decimal, you must remember to add the decimals. Then divide it into 1 to find the total resistance. Now, another situation that you may run into is a parallel circuit where the resistors have equal values. Here we have 6 ohms, 6 ohms, and 6 ohms. This formula is used in solving total resistance in this case. Here you divide the resistance of one resistor, 6 ohms, by the number of resistors, the N. In this case, you would divide 6 ohms by 3 and get a total resistance of 2 ohms. Of course, the more you use the formulas, plugging values in, solving for total resistance, the more you'll become familiar with them, and you'll find you'll have no problem solving for total resistance. Let's go over the power dissipated in a parallel circuit. The power dissipated here is very similar to the power dissipated in a series circuit. Of course, in a parallel circuit, the branch currents may be different. So when you're solving for the power dissipated by a branch, be sure to use the current flowing through a branch to determine the power dissipated by that branch. Now, any of these formulas may be used to solve for the power dissipated by a branch. The total power dissipated by a parallel circuit is equal to the sum of the power dissipated by each branch. Let's go over some important points to remember about a parallel circuit. The applied voltage appears across each branch. There's more than one path for current. Total resistance is always less than the smallest branch resistance, and the total power dissipated is equal to the sum of the power dissipated by each branch. If we compare series and parallel circuits, we come up with a couple of interesting facts. A series circuit has the same current but divides the applied voltage. It's a voltage divider. A parallel circuit has the same voltage but divides the current. It's a current divider. Okay, let's go over a bridge circuit, a circuit that's a combination of series and parallel resistors. Now, you should remember that a bridge circuit is basically a parallel circuit with 2 series resistors in each branch. It usually has a device to detect the magnitude and direction of current. For example, if I plug this galvanometer in here, we've bridged the circuit. We'll use the galvanometer to detect current across the bridge. You should also remember that a bridge circuit can be balanced or unbalanced. Let me close this switch. If the bridge is balanced, no current will flow from here to here. Notice that the meter is indicating 0. No current is flowing. The bridge is balanced. If the circuit is unbalanced, current will flow across the bridge. Now, the simplest way to determine if the bridge is balanced or unbalanced is to use a ratio relationship. If the ratio of R1 to R2 is the same as the ratio of R3 to R4, the circuit is balanced. Now, in this circuit, R1 is 1/2 of R2. R3 is 1/2 of R4. These ratios are equal, so this is a balanced bridge. Now, if any of the resistor values are changed, the ratios are no longer equal, and the circuit becomes unbalanced. Now, let me remove this sign because I have a rheostat here, and by changing this rheostat, I can upset the ratios and show you that the circuit can become unbalanced. So let me turn the rheostat so that current is flowing in that direction, to the right. Now, all I've done, I've upset the ratio so that current is flowing from this point through the meter to this point. So actually, current is flowing from here to here. If I change the rheostat in the opposite direction, I can cause just the opposite effect. Current is now flowing from this point through the meter to this point. So current is flowing from here to here. Now, all I'm doing when I upset the ratios like this is changing the relationship of the voltage drops across each resistor. For example, in the present condition, this point is negative with respect to this point. So the current is flowing from negative to positive. When I go in the opposite direction, so that current is flowing in this direction, really I reverse these two polarities. This point is now positive with respect to this point. So notice then that with a single control, this rheostat, we can cause current to flow in either direction across the bridge. And of course, we can vary the amount simply by upsetting the ratios more. Now, this feature of the bridge circuit makes it extremely valuable in applications such as weapons control systems, antenna positioning, measuring devices, and systems where a high sensitive control circuit is required. Now, we've covered series and parallel circuits, two of the basic configurations used in electronics. A thorough knowledge of how they work and what they do is essential before you can go on to more complex circuitry.